from MP15. Today we're gonna talk about transition metal dichalcogenides. Let's get started.
What is transition metal dichalcogenides? TMDs are materials of the form MX2, where M represents a transition metal atom sandwiched between two chalcogen atoms represented by X. All materials in this family are semiconducting as they have band gaps. These band gaps are direct in monolayer form and indirect in the bulk materials. This is due to the changes in electronic structure induced by quantum confinement. For that reason, they can be tuned into a conductor or an insulator.
Good morning, Doctor. How are you? We are here today with you to discuss about the tuning methods for TMDs.
I'm fine, thank you for inviting me.
We had questions sent in for this Q&A segment. The first one is regarding the strain engineering. Can you explain what it is all about?
Well, strain engineering is understood as the field that studies how the physical properties of materials can be tuned by controlling the elastic field strains applied to it. It's suitable for tuning the electric properties of TMD.
See, how exactly can it be tuned?
There are 5 methods of tuning, namely bending a flexible substrate, elongating an elastic substrate, piezoelectric stretching, substrate thermal expansion, and controlled wrinkling.
Shall we take a look at them?
The 2D material is deposited onto a flexible substrate. Stretch the topmost surface by bending the substrate. This transfers an initial tensile strain on the 2D material. The van der Waals attraction between the 2D material and the surface of the flexible substrate is strong enough to clamp the nanosheet and prevent spillage for strain levels up to 1%. Beyond that, sheets tend to slip and release tension. To reduce the spillage issue, one can evaporate metal strips onto the nanosheet. These act as clamping points.
So, what is piezoelectric materials? Piezoelectric materials are materials that respond to external electric fields. Piezoelectric materials is basically materials is elongated in the vertical directions and shrink in the horizontal direction when an electric field is applied. Electric field is applied through application of bias voltage between two phases of the piezoelectric material. I'm going to show you how piezoelectric material works. Is when external electric is applied, piezoelectric materials become shrink. So, in another way, it will cause the piezoelectric materials to elongate vertically. So this applies a uniform compressive biaxial strain on the material. The deformation of substrate can be easily regulated by varying the applied voltage. A trilayer MOS2 was transferred onto a piezoelectric substrate. Apply a bias voltage to the substrate, that surface where the flake is shrink. This subjects the trilayer MOS2 to a uniform compressive biaxial strain.
2D materials typically have negative thermal expansion coefficients. Substrate can be intentionally selected to have a very large positive thermal expansion coefficient. This is to apply a stronger uniform biaxial tensile strain on the 2D material.
Non-homogeneous deformations can be generated by wrinkling process. This is possible when transferring 2D materials on elastomeric substances. A thin film is deposited onto an elastomeric substrate that has been uniaxially deformed. The flexible substrate strain is released. This leads to a uniaxial compression of the thin film. When initial strain is below a critical value, ripping occurs. Ripping is deformation of thin film upon compressive strain. When initial strain is above a critical value, wrinkling occurs. Wrinkling is the elimination of thin film from substrate forming wrinkles that accumulate deformation separated by unstrained regions.
Wow, that's a lot of tuning methods.
Indeed, TMDs that can be stretched much farther than conventional material is opening the doors to new discoveries on application of these materials.
I see. So what are the advantages of using TMD?
Transition metal is better than graphene. It can be turned into a transistor for the use in small electronic devices. TMDs also have a large specific surface area due to sheet-like structures, which make it highly attractive for capacitive energy storage and sensing applications. The large surface area to volume ratio improves the sensitivity, selectivity, and lower power consumption of TMD sensors. Furthermore, 2D TMDs atomic layers can be easily isolated and stacked with other TMDs to construct a wide range of van der Waals heterostructures.
That's interesting, but what about the disadvantages of using TMDs?
Well, developing TMDs in large-scale and defect-free atomic players with thickness controllability on desired substrate is challenging. The quality of 2D TMD has not yet reached that of a mechanically exfoliated 2D transition metal dichalcogenide flakes.
So, what are the effects of tuning TMDs?
It changes its electronic properties, physical structures, and its bandgap depending on the type of strain applied. It can also affect the amount of charges flow in the compound.
2D TMDs materials are considered attractive for diverse applications. This includes electronic, photonics, sensing, and energy device. This is inspired by the unique properties of layered material, such as thin atomic profile, tunable electronic structure, optical transparency, and sensor sensitivity. Of particular interest for flexible nanotechnology, it comprises a wide array of scalable large area device. This includes thin film transistor, display, sensor, transducer, solar cell, and energy storage on mechanically compliant substrates and biosensor.
Alright, that's all you're gonna need to know about TMDs. Hope it can be beneficial to everyone. Thanks for watching!